Hi. So, continuing the streak, we are starting with um, last class we studied buffer pool managers and what are buffer pools and what usages that what is the use of buffer pools in database management systems. So, what you have is paid databases, they are just files on disk, and yes, so they're just files on disk, and what you do is you read those files into memory and you have a special software that's your database management software which knows how to read and write those particular files. So the file format for each database is unique to that particular database. So you cannot import like Postgres files and expect MySQL to read it or vice versa. And they all have their own formats of how they write data, how they write pages, and what organizations or what flags do they use. So what we'll do today is we're going to keep this short. We'll study about buffer optimizations, a bit of buffer optimizations, and we'll read about different storage architecture. Uh, so we know something. There's a storage architecture called tuple-oriented storage, where you store data as tuples consecutively in one page. Then you have index organized storage where your actual data is in form of a tree. You can traverse that B tree or any tree structure, and you'll eventually it will lead you down to your data. The last storage is very fascinating. That's the log structure storage. So this idea was born out of the fact that writing sequential files is much faster than doing random writes. So when you are writing a log, so you can just append to the end of the file. So if your uh, if your database management system uses a similar approach, then you can make a system that is very efficient at writes, but we'll see that how read performance might take a hit in that case. So we read about some buffer pool optimization in last class. We read about multiple buffer pools that you can have multiple buffer pools per table, per database, or you can have special buffer pools like for sequential scans. You can have circular buffer pools where you are flushing in pages and you're putting those pages out back out when you don't need them. So in to avoid polluting your main buffer pool and the eviction algorithm. Then you could do something known as a prefetching that you can predict that what page is going to be accessed next, depending on the access patterns, and uh, you can go from there and prefetch some of the pages for the query. Then you can do scan sharing where one query is running and it is reading a bunch of data, and while reading the data, it reads in pages. The some other query comes along, and what it does is it tries to uh, it needs the same data. So you piggyback that query on top of the first query and you read the data along. And when it finishes, then it can go back and read the pages that were remaining. So we saw this. We're not going to discuss this now because we saw this in the previous slides. What we'll do is we'll start with the storage structure. So, what did we do previously? We saw that how databases were laid out on disk. They were just files. And depending on how you're implementing your database system, you can decide that how I want to break my file into small chunks. Or do I want to use multiple files for multiple databases? Do I want to use one file for all the databases? Like for example, SQLite, they will use one file and they'll have multiple databases. Like you'll have the file broken into pieces so that it can contain multiple databases in one file. But you can also do multiple directories and multiple files for, you can have one file per table. You can have multiple files per table, per index. You can do all sorts of things depending on how you are implementing your system. So the structure of files matter that either if you are writing to one particular file, then obviously there might be more contention when you are writing to similar to the same block and you have multiple writers. Like SQLite has one writer, so there's not a lot of contention because it's just one writer trying to access the blocks. Um, Anyways, what did we see? We saw that how pages are laid out on disk, that you have files, and files can be broken down into pages. Pages, what are pages? Pages are just fixed byte chunks, which your file is broken into, and you read one page at a time from that particular file, and you put it in your workbook pool, and that particular page might contain tuples, or it might contain some internal data structure if you're dealing with indexes. So we also dug into how these pages are laid out, that you have tuple-oriented, you have slotted pages where there is a slot array in the beginning, and you have tuples being appended from from the end of the page. And what it helps you that you any outer data structures like indexes and any other data structures that are pointing to that particular tuple can just point to the slot array, the slot in the slot array. And internally, you might be able to arrange the page, uh, but you don't need to inform the outside world that I'm arranging the page. You might just want to, you will just have to point the slot array to the new offset, and the outer data structure will still be just pointing to the slot in the slot array. I hope I'm making sense at this point. But so what did we see previously? We presented a disk-oriented architecture where DBMS assumes that primary storage location is on the non-volatile disk. So we're dealing with file-based structures. We're not dealing with systems such as Redis, which they also have persistence options. But for these particular lectures, we are just assuming that we are dealing with a file-based system. We discussed a page-oriented storage scheme for organizing tuples across heap files. So we talked about the page structure, that you have slotted pages, but on top of that, we also discussed that how what page structure will you have, not the internal page structure, but how in a particular file your pages will be laid out. So if you have a file and you have a bunch of pages in that file, pages are what? Nothing but byte chunks of that particular files. So if you have a file and you have these pages, so what a page-oriented storage scheme is that you say that either these pages make no sense, that you have no order, you as you are inserting tuples, you find a free slot and you insert it. So these pages are random, and you have some external data structure which is keeping a bookkeeping for you, that where a particular tuple is lying in this data structure. Or you can say that these particular pages are holding a tree structure. So you can define some order between these pages. This order has to be uh, on the disk they are just bytes, but if you write a higher system that is able to interpret the logical ordering of these of the pages, then you can have something that makes sense, that you are dealing with a logical data structure up top. So, yeah, so what did we study? We studied tuple-oriented storage. That was the heap organization. That what you do is in a file, you just find a free page and you insert a tuple there. Today, what we'll do is we'll study about index organized storage, where the pages itself, they will hold some order as so. What benefit that gives you is that you might not have to maintain an external data structure. You might still have to maintain it for secondary indexes or even for a primary index, given that how your database internals work. So what do I mean by that is if your database is using the primary key supplied by you, then the pages will be laid out based on that primary key. So let's say you have emails and you're designing this database system in MySQL. MySQL has tree index organized storages. So if your database system just uses your supplied primary key as a key for organizing this data structure, then you might not need an external data structure to find data in this particular structure. But if your database system uh, manages to issue a synthetic ID to maintain some structure in this database, in this data structure. So what do I mean by that is you're supplying a primary key like an email address, but the database is not treating that as the primary key for building this page structure. Your primary key will build a separate data structure which will just point to this particular data structure. And how this particular data structure is organized, it might be that the database is internally manufacturing a primary key and you are building a primary index on top of that. But anything that the user says that is the primary key, so like if I say that the email is the primary key, that is not actually the primary index, but that might be my secondary index. Although logically it is my primary index, but on a lower level at the physical level, that is a secondary index, which is built on top of my primary index. I hope this is making sense. But so today we'll study index organized storage and then we'll touch upon log structure storage. I don't think we'll be able to get too far. Anyways, so just to give a recap, we studied slotted pages. What are slotted pages? That inside a page, you have this slot array with a header that contains checksums and other information. And each slot will point to some tuple in the page. Any external data structure, like a B-tree index, let's say you have a B-tree index here, B-tree, will point to this particular slot. So if you have to compact this particular page, then what you can do is you can bring it into memory and you can compact the whole thing. Like you can move tuples around. Like I'm, if some tuple is causing a fragmentation, let's say there's tuple here and there is this empty space, then you might want to move things around to compact it for better efficiency. Then you don't need to modify the B tree up top. Why? Because the B tree is still pointing to the slot array. And if I'm moving tuples, so let's say my slot 2 was pointing to tuple 4, and during my compaction, my tuple 4 has moved to some other location. Let's say now it's here. So I don't need to update the B tree. I just need to wipe this pointer and I need to point it to the new address. So I compacted the page, but I don't need to notify or I don't need to do a write amplification for other data structures to notify that the position of the internal tuple has changed. So, this gives you some control over that. You can modify the page internally, but you don't need to notify the outer world about it. Okay, so this is a valued argument also for MySQL and Postgres because Postgres uses heap structure storage. So you have external indexes which point to the. No, this is not actually a good argument. But anyways, so as you can see, the slot array is pointing to tuples. And as you add tuples, then you add the slot array, you extend the slot array also. And when they meet at some point, then you declare that the page is full. So let's say I'm deleting page tuple 3, then this will this will cause the page to fragment, and I can just move the tuple to the right and just extend this pointer to the new address location. Uh, What are these pointers, by the way? They are nothing, they are just numbers. So let's say you have a 4 kilobyte chunk. You bring this 4 kilobyte chunk into memory, and you can treat it as you are dealing with 4096 bytes of an array. So if you read, let's say it is at some index. Let's say this particular slot is lying at index 1000. So you go ahead, read that index out from that array, and you interpret that where is it pointing to. Maybe it is pointing to 2043, 46. You're pointing to that particular offset. What do? You just jump to that particular location in that array and you read out data. Okay. So we have something known as record IDs. So this is what I was talking about. Like, how do you have this is something the database generates for you, that it is a record identifier that represents a tuple's physical location in the database. So how do you make a record ID? You can use the file name, the page number, and the slot number. So that those three informations will give you the exact location of a tuple. So in ingress, that was the uh, what do you say, ancestor? Yes, ancestor, I think. Yeah, which was like ingress became Postgres, right? So ingress it issued something known as TID. Postgres issues CTIDs. SQLite issues row IDs, and then you have other databases issuing their own keywords. So what you can use these CTIDs to see that where exactly a tuple is lying. So your indexes in let's say in Postgres, I have an index and it is pointing to, let's say I have a B tree index. And when I traverse that particular B2 index in the leaf nodes, what I'll get a pointer to the CTID. What the CTID will tell me, it will tell me that where do I exactly need to jump in a particular heap file page to find that given tuple. So CTID is a combination of a file ID, a file name, a page number, and a slot number. Those three should be sufficient for any database system, unless you're doing directory stuff. If you are dividing your database into multiple directories, also then you might have to store locations, store the information about the directories too. So tuple-oriented storage are great at reads. Why? Because you can have these external data structures, B trees. B trees are a magic in computer science. You can have these data structures, B trees, which you can traverse, and even directly jump to the tuple the tuples you want. But prerequisite for that, you will have to have an index built on top of that particular column which you're looking up. So how do you get a tuple using its record ID? So you'll have record IDs. These record IDs you can sometimes access on the user level, like Postgres. For Postgres, you can issue a select CTID command, select CTID from some table, and it will show you the CTIDs of all the tuples in that table. You'll have these tuples of 01, 02, 03. So what are these? This is the page number and this is the offset, the slot array offset. I think I have recorded a tutorial for this. Not very sure though. Okay, so check the page directory to find the location of the page. That exactly where, if you have fixed size pages, then it's easy that if you have the record ID, that will contain the information of the page number. And if you have fixed size pages, you exactly know that if I multiply this page number by the given page size, then I'll jump to that particular offset in the file and you'll get to the location of the page. Then what do? You retrieve that page from the disk into memory, that is your buffer pool, and then you find the offset in the page using the slot array. So if you have the record ID, that record ID contains the information about the page you are looking to. So you bring that page in, and then that record ID also contains information for the slot you're looking to. So in that particular page, you jump to that slot, and in that slot, you follow the pointer and you read the data out. So the database management system relies on indexes to find individual tuples because the tables are inherently unsorted. So in this particular storage, in a tuple-oriented storage or a heap-oriented storage, you push in tuples randomly. You don't have any order while you're writing them to the files. Like Postgres does this. You don't have any order. Like if I insert, let's say I have a single parameter object that is ID. I just have this table, which is just an monotonically increasing ID. We have 1, 2, 3, 4, 5, and so on. So if I insert 5, then it will get inserted in some page. But if I go ahead and insert consecutively up to 1,000, then those will also get inserted into some random pages, right? Usually consecutively. But if I delete 5 and then I reinsert it, then 5 might get appended to the end of the page. So you don't have any order. You are not telling the database management system, like you're not telling the file system that I need to put this particular tuple as some particular location. You're just putting it where you can find a place. So when your files are unsorted, your pages are unsorted, what do? You maintain high level structures, your indexes, to tell you that either you do a sequential scan on the whole page, on the whole table, that you read the whole file and you do a sequential scan and you pull out the tuples that you want, or you use indexes to guide you where you exactly want to go. So what if the database management system could keep the tuple sorted automatically using an index? So what I'm saying is that when you're inserting, you don't insert randomly, you follow some order, and that is where we reach the index organized storage. This this guy is beautiful. Why? Because the initial idea of indexes was you have some raw data, you have some data, and you build an index on top of it. Now, index organized storage brings out the idea that you can have your data built inside an index. So your data is an index, and if you're inserting data, that might be slower than randomly inserting it anywhere because you might have to do lookups. But still, you are getting the benefit of ordering pre-hand rather than how do I put it? So, um, I have a lot of things going in my mind. I have write amplification going on right now because in Postgres, if I'm writing a tuple and I have 1,000 indexes that are pointing to my table, then I will have to go update 1,000 indexes. That's write amplification. That for one write, I'm doing 1,000 writes. But for index organized storage, if um, hmm, if I insert a tuple and I might still have to do 1,000 writes, though. That's a thought worth pondering upon. I think I'm gonna stop here. We'll touch this index organized storage next time. Wait, what? These log structure storage too? Compaction, compaction, conclusion. Oh, there are less slides in this actually. So 92 slides. Yes. I think we can cover index organized storage, right? How many two slides are there? One. Yeah, let's do it next time. So I'll see you with index organized storage next time. I do have an argument for MySQL and Postgres that how I think Uber did it that they were tired of write amplification that the all the indexes point to the physical location of the tuple in Postgres. So when they updated a row, then Postgres internally maintains these multiple copies for uh, for different transactions. And I think what they were doing was they had too many indexes, and for those indexes, they were pointing to physical locations of the tuples on disk. So if you update one tuple, then you'll have to go and update all the indexes. Then they switched to MySQL, and reasoning they gave in their blog, I'm not very sure, but I think the reasoning they gave was that MySQL points to the primary index and not the raw data. So when I'm moving tuples around in the first of all, MySQL will not maintain multiple copies. So when I update a tuple's location, then I just change that particular primary index, and my secondary indexes just don't need to know about that, because when somebody comes along and searches along the secondary index, they will just jump to the primary index eventually to find that particular tuple. I think that reasoning is right. In my head, it is right. I'll still have to look up that blog, Uber blog actually. Anyways, I'll see you around.